what I can do. If that came out right, you saw my image move across the screen. Cool, things you learn. So, today we're going to be learning about thermal energy and how to transfer thermal energy. Today is all notes, no worksheets. Alright, because there's a lot of notes to cover and I don't like cutting it up. So, here we go. Hopefully you printed out what you need, or you're looking at it while you're looking at this, or you just have a piece of paper and start writing stuff down. Your choice. So, thermal energy. That's so hot. Yeah, anyways. All matter is made of tiny particles. So to understand thermal energy, first you have to understand the kinetic theory of matter. All matter is made of tiny particles. We now know they're atoms and molecules. That's what we call them. Those particles are never still. So in the notes, those particles are always moving. Some people actually write always, never, still. Okay, fine. As long as you know what it means. Whatever. Even if just vibrating in place, they're always moving. And objects that are moving have what kind of energy? Kinetic energy. Okay. So, that's the kinetic theory of matter. Now I can define temperature. Because it depends on the understanding you just developed that all of your atoms and molecules have their own kinetic energy. Because they're moving. Even if they're just shaking in place, they're still moving. And yes, it's snack time for me, so I'm eating my snack too. Temperature is the average kinetic energy of all the particles of an object. Pause, write it down, come back. Yes, I have a liquid near my computer. It's just how I am. Sometimes it just be that way. Alright, we measure temperature in kelvins. You already knew that. And let's see if this picture makes any sense to you. So let me move my picture out of the way. I'm up there now. I can look down here to see the picture. Anyways, so you have cold and hot. They're still vibrating in place. Looks like they're shaking in place. But these are shaking more. They're spread out more. Why are they spread out more? Because they have more energy. They're hitting each other harder and bouncing out further. Your molecules do the same thing. When you're cold, they're closer together. When you're warm, they're further apart. You actually expand when you get warmer. I didn't say you get fatter. Don't go home and say, Mommy, I'm fat. No, I didn't say that. You expand. If you wear rings, like I do, because I'm married, you find that it's easier to put them on in the morning and take them off in the morning. You just wake up than it is later on in the day. I mean, not greatly harder, not greatly easier, but you can notice a difference if you pay attention. Throughout the day, you're warming up. You're moving around more. You're gaining more thermal energy just from your own internal processes. And so you expand a little bit. At night, you cool off a bit. You contract just a little bit. You still weigh the same. Don't go there. All right. Let me move myself back down here. And do that. Yeah, that's Lord Kelvin. I still have beard envy. Alright, so knowing this, what does it mean to increase your temperature? It means that your particles have more kinetic energy, so your particles are moving faster. If you're hotter, your particles move faster. Okay? Alright. Now I can define thermal energy. Thermal energy is the sum of the kinetic and potential energy of all the particles in an object. I know it doesn't really make sense yet because I threw in PE, potential energy. Just write it down and I'll explain. Okay, you got it? Good. Now, how do I explain potential energy? You know what? I'm not even going to bother with it. If we're in a classroom, I can do a demo. We're not there. Don't worry about it. It won't be on the final. Or are you going to have a final? I don't know. Gee, I hope not. That'd be annoying to me to give you and for you to take. Very annoying. Okay, so on the notes, it says something about 2 ways to increase thermal energy. 1 and 2. I'll make it bigger for those of y'all using your phone. 2 ways to increase thermal energy. 1 and 2. Okay, let's talk about them. First way to increase thermal energy is to increase the kinetic energy of the particles, which means make them hotter. You raise temperature, you raise thermal energy because you're raising the Ke part of it. What about the second way? Read this, see if it makes sense to you. More mass also means more thermal energy. Why? And here's why. There's why. If you have more mass, you have more particles. Move me out of the way. There we go. More particles means more kinetic energy and potential energy to add together. So basically, if I had a mug of coffee, I'm not drinking coffee right now, I'm drinking something cold, but if I had a mug of coffee right now, it has a certain amount of thermal energy, kinetic and potential energy. If I compare that to the thermal energy of an iceberg, you know how big icebergs are. They can take out big ships like the Titanic. They're big, they're huge. The iceberg, though it's way colder, would have more thermal energy because it has more mass, more particles to add up their Kes and Pes. Even though each particle has very little Ke because it's barely moving because it's cold, you've got trillions more particles to add up. So the iceberg overall would have more thermal energy than a cup or a mug of hot coffee. Temperature and mass both control thermal energy. Okay? Okay. And move me back down there again. And boom. Next thing is the word heat. Heat is thermal energy that flows from higher temperature to lower temperature. Oh, excuse me. Since it is a form of energy, we measure it in joules. You can just add somewhere in joules in parentheses if you want to, or not. I don't care. Pause if you need to. Finish writing that down, and then come back. Okay, you're back. I wanted to show you. Picture down here. The blacksmith. There's his forge. The G and the E got taken out by the hole puncher, but there's a forge. And there's the anvils. You know it's a blacksmith. There's his hammer. You know it's a blacksmith. Smithing a sword. You get the metal hot so you can shape it. It gets softer when it gets hot. Don't melt it, just soften it. Then once you get the right shape, you quench it in water. So when you put the sword in water, the thermal energy is flowing from the sword out into the water. The red hot sword is quenched in cold water. It loses thermal energy. Its temperature goes down. The water temperature goes up. Okay, so you've never made a sword before, probably. But you've experienced the same thing. You touch something warm to warm yourself up. Okay. Sword temperature goes down, water temperature goes up, and if I leave the sword in the water long enough, they'll continue to do that, exchanging heat to the water until they're both the same temperature. Heat stops when the two objects are the same temperature. It can't flow, because it always flows from high to low. If they're both equal, it can't flow anymore. That makes sense? Good. Okie doke. Get shrinky, get ready, and boom. Cold is not a thing. It is a lack of a thing. You can't transfer cold from one object to another, but you can transfer thermal energy from one object to another. That's what heat is. So if you touch an ice cube with this ice cold mug, my hand is getting cold. It's not putting cold into me. I'm putting thermal energy into it. I'm losing temperature. So my hand gets cold. Cold is not a thing. It's a lack of a thing. Now my hand's cold. It's kind of like a hole. We know what a hole is. Take a shovel, Move some dirt, you have a hole. Can I pick up the hole? Can I carry the hole? This is not a Bugs Bunny cartoon, so no. A hole is not a thing. It is a concept, an idea. It is a way to define something missing, a lack of a thing. Cold is a way to define a lack of a thing, a lack of thermal energy. Okay? So you cannot transfer cold to something else. You can only lose thermal energy or gain thermal energy. If you're losing it, you get what we call cold. If you're gaining it, you get hot. Heat always wants to move from warmer objects to colder objects. So two objects touch and at different temperatures, heat flows from the hotter one to the colder one. Always. It's natural. It's just going to happen naturally. Just like if you let go of a pencil and it falls to the ground, it happens naturally. Once temperatures are equal, get my face out of the way, no more heat is transferred. Okay. This concept is specific heat, and there's a definition. Write it down. Can I get out of the way? There, I think I'm out of the way. Specific heat is the amount of heat it takes to raise the temperature of 1 kilogram of a substance by 1 Kelvin. That was spooky. I think my wife closed the door. Got that written down? Didn't have to pause or anything? No? Good. So this last part here, if you remember, 1 Kelvin is the same size temperature scale as 1 degree Celsius, so same thing. Alrighty, so what? Who cares? Well, put that back up there. Some things will heat up quick if you leave them out in the sun, like your car hood, or any piece of shiny metal, any piece of metal, period. Metals have very low specific heats. So if you put just a little bit of thermal energy in them, temperature goes way up, because it only takes a little bit to raise their temperature. Water, on the other hand, if you've been to the beach, and I know you can't go to the beach right now, I know, but if you've been to the beach in April in years past, the beach can be fine if it's a nice warm day, but the water, cold, which some people like, more power to you. Why is that water cold? Because water has a high specific heat, way up there. It takes a lot of energy to warm up water. So it takes months of sunlight bearing down on it every day to warm up the water at the ocean. Also takes months for it to cool it, for it to lose it too. So that water stays warmer in the wintertime, warming up our coastal regions. If you ever notice, the temperature on the Outer Banks is warmer than temperature here in Wayne County during the winter months. Don't believe me? Remember this 6 months from now and watch the weather. Yeah, like you're going to watch the news. Whatever! But if you do watch the news, thank you. You're awesome. If you don't, start. Okay, so basic knowledge everyone remembers from high school science class, even your parents, yes, them too. All metals have low specific heats. Water has a very high specific heat. Low specific heat means it heats up easily and it cools off easily. High specific heat means it's much harder to heat it up, and once it's hot, it's much harder to cool it down. It takes more time. Okay, ignore this because you ain't got a book with you. You ain't got a book with you. You ain't got a book with you. Okay, whatever. So, next thing, coolants. Let's see here. These notes are, well, you probably printed out two-sided, or whatever. Find a spot somewhere and write down what coolants are used to do. They're used to cool things down, unless you already knew that, in which case you don't have to write it down. So coolants are used to cool things down. Let me move my face back down over here. Okay. Would you want your coolants to have a low or a high specific heat? Think about it. Just think about it. Pause and think about it. Did you think about it? What'd you think? The answer is you want your coolant to have a very high specific heat. you want it to suck as much thermal energy as it can into itself before it goes up a degree. It's kind of like the water and the sword. The metal has a very low specific heat. If it loses a few joules of thermal energy, it goes down a lot in temperature. The water has a very high specific heat. The same number of joules of energy going into the water won't warm it up that much. Remember, heat flows until temperatures are the same. But if the temperature of your metal goes down really fast as the water goes up just a little bit, they meet at a very low temperature, which is what you want for coolant to keep things as cool as possible. So you want the coolant to be able to absorb more thermal energy and warm up very slowly, much more slowly than what you're cooling off. Water is a great coolant. Naturally speaking, it's the best coolant in the world. But of course, we've got other ones. I know y'all gonna get confused. You call it antifreeze, but nowadays, modern day antifreeze has coolant mixed in it. So, put antifreeze in your radiator and use it all year long. When I was a kid in the 70s, that wasn't the same way. You had to change it out. 6 months of the year, you had water in your radiator. 6 months, you had antifreeze. Crazy. You don't have to live in those times. Okay. Now we're on to the next page. If you want to take a bathroom break, go for it. Of course, you can do it anytime you want to, because you can hit the pause button. So can I, for that matter. But I won't tell you when I do. Alright, if heat is the transfer of thermal energy, how does heat happen? 3 ways. Conduction, convection, radiation. I even have 3 little sections for you on the notes to write it down. Or you're writing your own notes. What else? That's cool. It brings it down when you grab it. I'm learning things. Alright, so conduction, convection, radiation. I'm blocking the word radiation with my face. There we go. Alright. Conduction definition. Transfer of thermal energy by collisions between particles of matter. In other words, they have to touch. So conduction is touching. Kind of rhymes. Yeah, write it down. Pause if you have to. Let's move on. All matter can conduct. Even the air can conduct heat, but it's really bad at it. Solids are the best conductors. Of the solids, the metals are the best at best. Okay, there's an explanation as to why metals are the best conductors in the world. Look at it, learn it, don't learn it. Not super big. It's just people have asked in the past, so there you go. That's why. Something about the loose electrons. You do remember metallic bonding, don't you? Okay. Moving forward. Convection is the next we need to write down. Convection is the transfer of thermal energy in a fluid by mass movements of matter. Now, y'all going to be thinking, pause if you need to, then come back to me. Y'all going to be thinking that fluid means liquid. And yes, all liquids are fluids, but not all fluids are liquid. The only state of matter that is not fluid is solid. Every other state of matter is a fluid. Liquids, gases, and plasmas are all fluids. I didn't mention plasmas here because we don't deal with them very much in our everyday lives, but yeah, they flow too. A fluid is defined as that which can flow. Liquid and gas can both flow. You don't believe air can flow? Air can flow. Alright. It's getting up to 20 minutes. We gotta move on. I hate teaching like this. I wish I had a lava lamp. In fact, I'm gonna put a lava lamp. I'm gonna find it somewhere on YouTube, whatever, and I'm gonna attach it to this thing. Alright. But in short, as heated fluids are heated, hot things rise due to differences in density. And so what you have here is at the bottom of this container, the flame is heating up this liquid, and this little blob of liquid rises up. doesn't leave a hole down here. The cooler fluid comes in from the sides, fills it in. Alright. So the cooler fluid flows into the space that the hot fluid is occupying. That's the little cold water sinking thingy. But now it's at the bottom. It's at the heat source, so it heats up. And it rises. And the cycle continues. Up, to the sides, down, up, to the sides, down. Let me show you. Like that. Here's the heat source. Boiling up, sinking down the sides, heating up, rising up, sinking down the sides. If you've ever boiled spaghetti, alright, look down on the pot. Don't get right over it, the steam will burn you, but look down on the pot. It's like looking down this. The spaghetti rises up in the center and goes off to the sides. And it gets when you get a good boil going. Alright. The last way is radiation, the transfer of energy by electromagnetic waves. More on the electromagnetic waves later. Conduction and convection need matter to work. Radiation does not need matter at all. Radiation is how we get heated up by the sun. Sun's rays shine down from, isn't it 800 million miles away? It's a long ways off. It takes light 8 minutes to get here. And light travels pretty fast. And yet, the sun is so far away that it can burn me. In fact, it did a couple weeks ago, and I'm still peeling from it. I don't know if y'all can see that or not on the camera. Actually, you probably don't want to see that. It's fairly disgusting. But anyways, yeah. The joys of being pale. So radiation does not need matter to work. It can go through the cold vacuum of space. Conduction, convection need matter to work. Alright. Radiant energy passes through gases easily. Radiant energy can pass through or be absorbed by most liquids. Most solids absorb radiant energy. Alright, you ain't writing that down, just think about it. Most gases are see-through. Light, radiant energy goes through them. Liquids, it depends. If you know anything about scuba diving, you know past 200 feet you need a flashlight of some kind. Because sunlight doesn't penetrate down further than that. The water will absorb it eventually. Solids, most do not let light pass through. Yes, I know there's exceptions. Glass. I know. It's a solid, but light goes through. But those are exceptions. Anyway. Now, we're down to the part that says insulators. As said before, all matter conducts, but some matter is really lousy at conduction. We call those types of matter insulators. Ooh, it froze. Why did it freeze? There we go. That was strange. So we're down here now. Doop, 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 doop. So what's the definition of an insulator? What's it? By the way, that's snow on the car, snow in front of the car, snow shovel, stick figure in a jacket with a toboggan on. Okay, you've seen it for that now. There's a definition of insulators. Substances that slow the transfer of thermal energy from one place to another. Okay, write it down. Done? Good. One of the best insulators is air. That's why you wear fluffy jackets in the cold of winter. Yeah, like we have cold around here, whatever. You want cold? Live in Montana, you'll know cold. That's why we have thicker blankets. Normally, thicker blankets are warmer. The fluffy ones. Okay? So any material that has lots of air in it makes for a good insulator. Feathers are a great insulator because they're hollow tubes full of air too. This pink stuff down here, fiberglass insulation, traps a lot of air. This is cotton insulation, traps almost as much air, not as much. Cotton's not as good, but it's a lot easier to deal with. The thing about fiberglass is it itches. Cotton, no itch. If that was fiberglass, she would not be smiling, she would be screaming. Alright, I'm going to skip this part right here because you don't need to know about it. So I'm going to end this right here. See. Okay, so that's it for the notes. Like I said, we're going to skip this part down here. I'm going to make it big for people on the cell phones. We'll skip this part down here about vacuum bottles, also in the thermos. Don't worry about it. Just whatever. And tomorrow, come up, there'll be some worksheets for you, alright? In the meantime, you're done. You stuck with me for 25 minutes. Thank you. I know it's hard to see my face for 25 minutes. Have yourself a glorious day. And I will see you when I see you. Goodbye.